Thank you for Chairman. Hello everyone, I am Nagahiro Fujiwara from Hiroshima University, Japan. My presentation title is Pixel Level Vibration Source Detection using Undersampled Video Sequences. Today, drone market is growing all over the world. Drone technology is expected to be applied to various fields such as logistics, measurement, agriculture, and so on. On the other hand, a threat of illegal drones are concerned, such as smuggling, boya, terrorism, and so on. So, drone monitoring system is required all over the world. Many drone detection methods have been proposed. One of them is method using acoustic sensor. But it is low accuracy to detect because sound is low spatial directivity. Also, there is a method using image. Most of them are based on a feature of spatial pattern. But they are not always robust with various factors such as apparent small scale, pose variation, complicated background, and so on. And there is other method using pixel level time series brightness variation. Drone's propellers are rotating at hundreds of hertz. It is much larger than other vibration source. So this method utilizes its vibration feature. That's why it is robust with various factors compared to other methods. However, normal camera cannot detect drone's propellers because most of cameras' frame rate is 30 FPS. It is much lower than propellers frequency. It is around 200 Hz. Left video shows drones captured at 30 FPS. We cannot see rotating propellers. Right video shows drone captured at 500 FPS. We can see them and observe periodic change. And this is related work. This is high frame rate vision based multicopter tracking. Drone's propellers are rotating at about 100 RPS, and images are captured at 1000 FPS. So this camera can observe rotating propellers because frame rate is much higher than object frequency. So as you can see, a high-speed vision is tracking a flying drone. In this research, the pixels corresponding to drone's propellers are extracted as vibration region using pixel-level digital filters. And this is drone detection algorithm using pixel-level short-time Fourier transform, hereinafter called STFT. Time series brightness signals at every pixel are acquired from high-speed vision. Then time frequency responses at every pixel is computed using STFT. And when peak frequency is in the range of assumed frequency, these pixels are extracted as vibration region. Although the algorithm using high-speed vision is high accuracy, computational complexity is high. So there is a limitation of detectable pixels in real time. So we can monitor drone in wide range by decreasing the frame rate of the vision system. So lower frame rate of the vision system is desirable as soon as possible. Then undersampling is a technique of signal processing where a high frequency signal is sampled at a rate below its next rate. We use this technique in order to realize lower frame rate of the vision system. So normal camera cannot detect object vibrating at hundreds of hertz. I explained it in previous slide. But correctly, if exposure time is short like high-speed vision capturing, periodic change is observed as areas at lower frame rate capturing. When capturing at 30 FPS, the pixels over 15 Hz are observed below 15 Hz as apparent frequency from sampling theory. And I'll explain undersampling more detail. We assume this is actual signal and frequency. So Nyquist rate is half of sampling rate. When actual frequency is smaller than Nyquist rate, so rate frequency is observed correctly. And when frequency is equal to Nyquist rate, actual frequency is observed correctly too. But frequency is actual frequency is larger than Nyquist rate. Frequency is observed below its Nyquist rate as apparent frequency. Next, I'll explain determination of undersampled frame rate. First, this equation shows the position of apparent frequency. And when F0 is here, F0 is actual frequency. Then when F1 is here, so F1's apparent frequency is here. And F2 is so too. And the position of apparent frequency can be changed by varying frame rate. And this equation shows the separable condition between two ranges of vibration source. When the difference of each frequency, each center frequency is larger than the sum of each frequency margin, two apparent frequency bands are separable. And above condition means separable condition is normalized. And this condition shows all apparent frequencies bands are separable. Thus, the minimum frame rate that satisfies the separable condition is searched and determined. And the next images are captured at determined frame rate. And time frequency responses are computed at all pixels using STFT. And peak frequency is searched in the range of apparent frequency. And last, the vibration region are extracted by threshold at peak frequency. And this is a simulation when two vibration sources are assumed. One is in the range of 0 to 10 Hz intended background environment. And the other is in the range of 208 to 228 intended drones propellers. We set the parameter corresponding to this environment. And the right graph shows the relationship between frame rate and separable condition. When the separable condition value is larger than 1, the apparent frequencies band can be separated by its frame rate. And below video shows the apparent frequency range when frame rate varies. Although two apparent frequencies bands are overlapping at this time, and but at 47.6 fps, two vibration sources are separable for the first time. And we did drone localization experiment to verify algorithms. This is a movie captured at 47.6 fps from simulation. A drone is flying in outside environment. And this is used drone and camera details. And this is the result of pixel level STFT at unchanged pixel and drone's propellers passing pixel. At unchanged pixel, there is no large power spectrum in the range of drone's apparent frequency. On the other hand, at drone passing pixel, peak frequency is detected in the range of them. And this is the result of STFT applied all pixels. Left slide shows input video and right slide shows vibration region video. And 60 by 60 ROI images are based on center of gravity of detected region. So we can see drone's propellers region is only extracted at the images. And this is the trajectories of drone based on center of gravity of detected region. Below graph shows changes of XY trajectories and the number of detected pixels. As you can see, we succeed in tracking the drone captured at 47.6 fps. And next, this is simulation when 3 vibration sources are assumed. So in addition to previous experiment condition, the other is in the range of 150 to 170 Hz intended drawn to the propellers. We set the parameter corresponding to this environment. And so So this is a simulation when frame rate changes, apparent frequency area is changing. And it is separable at 119.1 FPS for the first time. It is minimum frame rate in this parameter. And we did a drone localization experiment to verify proposed algorithm. This is a movie captured at 119.1 FPS from simulation. And two drones are flying in outside environment. They are rotating at different range of frequencies. And this is the result of pixel level at two drones propellers passing pixels. At drone 1 passing pixel, peak frequency is detected in the range of its apparent frequency, and drone 2 is sawtooth. And this is the result of STFT applied all pixels. Red region at output video shows drone 1 area, and blue region shows drone 2's area. We can see two drones propellers region are extracted as the image independently. And this is the trajectories of two drones based on each center of gravity of detected region. As you can see, we succeed in tracking two drones independently captured at 119.1 FPS. Although we need about 500 FPS camera in this environment experiment in the conventional approach, we can detect drone at much lower frame rate capturing. And this is summary. So we try to do accuracy verification of proposed algorithm. And we try to feedback control for variable frame rate. And application for other vibration sources such as bees, insects, and so on. Thank you very much.